And thank you very much for giving me this chance to introduce you to or update you on the AGORA project and what we have been achieved in the past years. So I just want to make it very clear that this achievement so far that we have made in the past 3 years would not have happened without the contributions of many people, already like 130 people strong in our collaboration, especially those some in the audience and including the people that I'm listing here who have made the major contributions in the past year. So before I begin, as I wait for some more people to come in, so I have been the AGORA project coordinator in the past, since its conception, like in 2012, and that's when I was a postdoc here at UC Santa Cruz. So I actually studied physics and got my degree from Stanford, and then I moved to here to Santa Cruz and spent about 2 years working with Joel Primack and also Mark Krummels. Then I went to Caltech and spent about 1.5 years. And I'm now back at Stanford. So this orbit, if you look at this orbit, then there is a clear indication that there must be a strong gravitational body somewhere around San Jose. And that's exactly where my wife has been working as a Silicon Valley engineer for the past 4 or 5 years. And it recently increased its mass. And this third body is even accreting more fluid and increasing more mass. So the escape velocity is like, yes. I mean, I don't know where I'm going now, but yes, but that has been my past. So enough about me. So going back to the AGORA project. So I'll try to answer 2 questions mostly, and then I'll try to convince you on 2 accounts whether or not you are an observer who doesn't care anything about what simulators do, or you're a person who have heard about AGORA project so many times so you're sick of it. So the first question is, why are we here? The AGORA initiative part of the talk. And the second part is the infrastructure of the talk. Where do we stand in terms of building the infrastructures and what you can do or what you can make use of it. So I'm a galaxy simulator. Galaxy formations are incredibly nonlinear at multiple different scales, spanning from massive black holes, accretion and feedback, to star clusters, formation and feedback, to intergalactic dynamic scale. So we all know that. And because the simulations are the only tools that we have in store to actually experiment with the galactic initial conditions and see what's happening in actual time, numerical experiments are really the only tools that we have to really experiment with the galaxies. So now I'm trying to define myself as an experimental, rather than just a fake simulator. So here you can see that you're using one code. You set up a suite of simulations, one using your favorite feedback physics. So that will be your experiment. And you compare that simulation with your control, say, without your feedback physics. Then you always compare those two and compare against the observed galaxies. Make sure that hopefully your favorite feedback physics works better to reproduce the observed galaxies. So that's what you should have in mind when you define yourself as a proper experimentalist, proper scientist. So now that I define myself as a proper scientist, I'm now abide by the principles of scientific method. We strive to make sure that our results are reproducible, verifiable, and falsifiable by doing all kinds of measures to make sure that our experiments and the scientific outcomes are robust. So we sometimes, as you can see, risk our lives to do it. So as a simulator, you must do it. So this must be the picture that you now can have. to verify that your success is scientific and robust, you always have to make sure that your experiment produced in, say, from one code platform must be compared against another set of experiment done in a independent, different code platform. So that's what you have to do compare across the code platforms and also against the observed galaxies. That's, I think, what simulators as a community has to make sure happens all the time. But this has been tricky, of course. It's because there are many different reasons, but I can go through, say, I guess 2 of them. It's really tricky to constrain to make sure that we are comparing apples to apples by constraining the exact same physics that's going into a different sets of simulations performed in a different code platforms. So, and sometimes it's the insufficient resolution that makes any physics, any subgrid physics, not working properly without enough resolution. So that's astrophysical inputs are not carefully constrained in any previous attempts to compare simulations across code platforms. And also another thing that I can quickly mention is that it's incredibly tricky to access to different simulation outputs. And if you're, say, a graduate student, unless you're an expert in, say, 5 different code languages, you always have to talk to individual person who actually ran the simulation and make sure that you are comparing apples to apples in any, say, radial density plot. Are you comparing the actually the same quantity across the code platforms? It's quite tricky. Imagine that. So against those backdrops in 2012, we initiated this AGORA project. As you all know by now, it's a collaborative multi-code platform to try to raise the predictive power of simulations as a community. So it's not, by joining the forces between, at the moment, 9 different code platforms, we're trying to raise the trust level, per se, trust level of the simulation community as a whole. So we have now about more than 130 participants from like 60 different institutions as of right now. So, and as you have heard, the first slide of the project has been published last year. So now we're talking about the AGORA infrastructure. So we want to make this project as not just a one-time love affair between different codes. Rather, we want to make it as a sort of a sustainable infrastructure, sustainable sort of shared idea where anybody can use the components that we have built in their comparison study or in their any study. So we are trying to build we have already built a common initial conditions, cosmological and isolated initial conditions, and we have worked with the YT community, having, say, joint workshops, and we're pushing them to make their YT code available and accessible by all these participating codes, including including most of the particle codes that are widely used in the galaxy formation community, including, say, gasoline, gadget, gear, gizmo, so on. So that's that part. And we also, we have developed, as part of a AGORA project, developed this package called GRACO that's going to provide the common astrophysics component that we all can agree on, like, say, for example, gas cooling or UV background. That's pretty much what we can already agree on. Maybe not star formation and feedback, not yet. But if we can agree on those components, we can outsource them to this GRACO package. And by doing so, we can make sure that we are already eliminating some sources of confusion or sources of discrepancy between different codes. So, and most importantly, we are trying to design this entire infrastructure and project with astrophysical questions in mind, so we can continue to use this infrastructure for investigating science questions, for example, like too big to fail problem, for example. If we can answer or find a solution using different code platforms and come up with a more or less consensus answer to a particular problem that we're experiencing in the community, then it may have a better predictive power or better, deliverability per se. So I will just quickly go through this, sort of going through the component parts. So the AGORA initial conditions, as I said, the cosmological initial conditions spanning in wide range of mass ranges and also two different assembly histories, one violent and one quiescent merger histories, are available for your experiment. So whether or not you're already involved in the AGORA project, you are free to use it for your own experiment. And it's actually good to use it because we are already releasing this initial conditions in a hope that we can already build a AGORA simulation library. So maybe you may not intend to do any comparison now, but just by specifying which initial condition you used, like those people that you're seeing right now in this slide, you are potentially allowing others or yourself to compare your results against others who have used the same initial conditions. So that's why we're already releasing the initial conditions. And as I said, the AGORA pipeline or the infrastructure, including the initial condition and the common analysis platform, has been put to a test in the dark matter only proof of concept in the paper last year. So you can see that 9 codes agree quite well in the dark matter only. That's what was expected. But the thing that I was hoping to emphasize here is that to make this plot, like joint composite radial density figure, this few lines of codes are all you need to access all different types of simulations. So this YT has been pushed by the AGORA side to achieve this kind of multi-code accessibility. So you're really invited to check out because it's really good. And I mentioned this already briefly, but the Graco package is now fully developed and implemented in all the participating codes, although it doesn't yet involve the full-fledged chemistry. The Graco has the capability of doing so, but not every code has imported that kind of capability yet. But it's now ready to be used in every single code that we have in our collaboration. So we're good to go to the baryonic physics regime. And that Graco package and another initial condition that I talked about, the isolated initial condition, isolated disk initial condition, is now put to a test in this effort led by Oscar Egertz and Roman Tessier here. So as you can see, this lists the 9 codes that are participating. This is a 1 million year, 0 million year snapshot, but it already means that the initial condition has been read and outputted by each of the code and read by the common analysis platform. Of course, I have a more involved figure, but I'm not. We did our best to buy this workshop to be able to make this figure public, but that hasn't happened. So we're gonna discuss this paper and the many figures that we have made in the past few months in the weekend session. So if you're interested, you're welcome to join. I just want to quickly name the names who put a great amount of effort to achieved this so far in the past year especially. So implementing Graco and running the isolated disk and helping all of us to analyze this properly in the common analysis platform. So to conclude, the answers are clear. So AGORA initiative is here to stay. It's not going to go anywhere. So you're all recommended to follow our suits and make sure that the simulations are reproducible by the independent minds in our community, in the same community as yours. And the AGORA infrastructures, it's almost ready, like 99% ready. You're welcome to check out, and if you're an observer, challenge your simulator colleagues to check this out. Thank you very much.
So maybe Valentina should come set up, maybe take one question. So I will ask a quick question. So you talked about the goal of trying to test sort of physics. You have all of these simulations you're implementing basically exactly the same physics, and you're going to make predictions. I mean, how does that actually help you learn new things? I mean, what you're doing is you're making sure all the codes give you the same thing. How does that actually help you learn new things about like what physics you can put in?
Right. So the part that you mentioned is only, I think I consider those part as like forming a careful baseline for a future comparison study. So in the actual science study that will be led by 9 different science working groups that Joel showed, will include like different feedback recipes or different ideas about how to model the star formation or what's going on inside the galaxies that we can not resolve. And then we are going to compare those based on what we already know about from this baseline study, that things has to be more or less correct if we were to include the exact same physics across the board. So yeah, I guess by doing this sort of 2-step approach, you can learn a lot.
Do you think at some step you won't need to run all X codes to do science, or do you always envision running all X codes?
I don't think it's not even practical or possible to ask everybody to be involved in all 9 science working groups. So, it'll be, per need basis, per volunteer basis.